Hello friends, welcome to our channel Crash Course for the Engineers. Let us go to the topics related to heat transfer. Today we are going to understand steady and unsteady state heat transfer. Let us take an example of a wall. Now you can see here there is a wall. Suppose this wall is having certain thickness. Now let us talk about the heat transfer from the inner side of the wall to the outer side. So suppose this is the inner side and this side is outer side. Now we are measuring the temperature of the wall at different time. So suppose the time t is 2 p.m. and we have measured the temperature of the wall. The inside temperature was found to be 15 degrees Celsius and the outside temperature was found to be 7 degrees Celsius. Now, because of this temperature difference, what we'll find there is a transfer of heat from inner side to outer side. Suppose this transfer of heat is Q1. Now, after some time, we are measuring the temperature of inside temp wall and outside wall. So, suppose at time T is equal to 8 p.m., we measured the temperature and we found out that the inside temperature is still 15 degrees Celsius and outside temperature is 7 degrees Celsius. So we have measured the heat transfer. Suppose this is Q2. Now what we are observing that the value of Q1 is equal to Q2. That is the heat transfer is not changing with respect to time. Okay, let us take another example. Now in this example, we have measured the temperature at same time, that is time is equal to 2 p.m. and time is equal to 8 p.m. And what we found out that the inside temperature was 15 degrees Celsius, outside temperature was 7 degrees Celsius at 2 p.m. and at 8 p.m. the inside temperature was dropped to 12 degrees Celsius and outside temperature was dropped to 5 degrees Celsius. So we measure the heat transfer in both the cases as Q1 and Q2. And what we found out that Q2 or Q1 are not equal. Now, what observations that we can get from this example is that the temperature term, the temperature inside the body, inside the wall, is not changing with respect to time. So temperature is not changing with respect to time within the medium. Okay, so the effect of time on the temperature is zero in this example. But in the second example, the temperature is changing with respect to time. That is, it will have a certain value. This is the second example. Okay, so these two terms are called as a steady state heat transfer and the second term is called as unsteady unsteady heat transfer. Now friends, understand that if you uh, read the concept of steady and unsteady state heat transfer, let us go to the unsteady state heat transfer. Heat transfer. Okay, so this unsteady state heat transfer are of two types. One is a lump heat transfer, and second may be called as a unsteady state heat transfer or steady heat transfer, or in other words, we can say it as a not lumped system. Now, let us take an example of lump heat transfer and unsteady state heat transfer. So, all the mechanical engineers know this process where the copper balls are kept in furnaces or ovens. Suppose I have a very small copper ball. Now we are saying that the diameter or the radius of this ball is very small. Now suppose the ball was kept in a furnace at 500 degrees Celsius. After that it was removed. Now what will happen as we are keeping this ball in the a- atmosphere where the material medium is air, so continuously it will reject heat to the atmosphere and it will start to cool. Now, if we measure the temperature of the ball, we will find out that the temperature at inside of the ball is a changing. So we are saying that it is an unsteady state heat transfer. But if we measure the temperature at various points inside the ball, we found out that the temperature is not changing inside the ball. So it means that suppose after reviewing the from the furnace the temperature was 200 degrees Celsius, then we'll get that the temperature inside the ball drops to 150 degrees Celsius. But at all the points inside the ball, the temperature is uniform, that is 150 degrees Celsius. The temperature is decreasing with respect to time. The temperature is changing with respect to time, but temperature is constant with respect to distance or radius inside the ball. After some time, suppose the time is 10 a.m. After 30, 30 minutes, we measure the temperature as 150 degrees Celsius. After at 11 a.m., we found that the temperature is 100 degrees Celsius. But the temperature is uniform inside the ball, or we can say the temperature is constant throughout the ball. So this can be called as a lump heat transfer, where the temperature is a function of time, but the temperature is not a function of distance. So I am saying that this distance is not having any effect on the temperature. Now this is the case when we are saying that the body is very small. Now take another example. We fry food materials. Okay, we Indians fry food materials. Okay, so suppose we have a chicken fried inside the oil and we remove it. So what will happen? So suppose this is the chicken, this is the inside surface of the chicken. Now when we check the temperature of the chicken which is removed from the hot oil, we found out that the temperature at the surface of the chicken is suppose 100 degrees Celsius, but as we go inside the chicken layer, we'll find out the temperature is dropping to 70 degrees Celsius, and at the center, the temperature may be 60 degrees Celsius. So suppose I measure the temperatures at in at 5 minutes, 5 minutes after removing from the oil. I found out these temperatures. At the surface 100 degrees Celsius, at the second layer 70 degrees Celsius, and at the third layer 60 degrees Celsius. After 10 minutes, what I am getting, the temperature at the surface may be 80 degrees Celsius. The temperature in the second layer it may be 60 degrees Celsius, and the temperature at the central layer is not changing. So what I can comment from this that the outer layer will reduce its temperature at a faster rate as compared to the inner layers. So we can say that the inner layers will be at a higher temperature. So this can be called as a unsteady state heat transfer, where the temperature is changing with respect to time and also it is changing with respect to distance. So this S factor is very important in case of the unsteady state heat transfer. So this is the difference between an lump heat transfer and unsteady state heat transfer. Now how to check whether any system or any body is experiencing a unsteady state heat transfer or lump heat transfer. Now there is a small derivation for that. Let us go to the derivation of lumped system analysis. So this is called as lumped system analysis. Okay, so let us assume any a body, a solid body of any shape, which is having m as the mass of the body, then v as volume of the body. Then suppose rho is the density of the material of the body, and let us say that Ti is the initial temperature. Okay, now so this is the body that we are talking about. Suppose AS is the surface area of the body, and this body is exposed to any fluid, or let us say the fluid is having the temperature T infinity and the heat transfer coefficient is H. Okay. Now, for the sake of convenience, let us assume that T infinity is more than the initial temperature of the body. Now, in the previous example, only we have discussed about the chicken which was kept in a frying pan. So let us, in the same way, we are seeing that the temperature of the fluid is more than the temperature of the body, that is initial temperature of the body. Now, by the laws of the thermodynamics, we can say that the heat transfer into the body in time delta T. Now, whatever the heat transfer into the body will take place from the outside fluid to the body, that will be equal to the increase in energy of the body, energy of the body during during time t. Okay, so the heat transfer will take place from the fluid to the body by the process of convection. So we know by the Newton's law of cooling, this heat transfer is equal to H into AS into the temperature difference. And that temperature difference may be equal to T infinity minus T. Okay. And in time, delta T. Now, increase in the energy of the body, increase in energy of body will be equal to mCp delta T. So mCp into delta T. Now, as we are saying that both the things are same, so we can say that H into AS into T infinity minus T into dt is equal to mCp delta T. But we know that the mass of the body will be equal to density into the volume, and also that the dt value is equal to d into t minus t infinity. So putting this value in the relation number 1, so suppose we are saying this is the relation number 1 and rearranging the relation, what we are getting, d into t minus t infinity divided by t minus t infinity. So keeping the terms of t minus t infinity on the same side, then we get is equal to h into as upon density into v into cp into del T. Understand that the notations are as per the heat transfer books. So small t refers to the temperature, small t refers to the time, and capital T refers to the temperature. Now, if we integrate this relation, and we know that what are the boundary conditions. So boundary conditions are very simple. Okay. So when time t is equal to 0, the temperature of the body will be the initial temperature. And when time t equal to t, the body temperature will be equal to T of at temperature at time t. So the integration of 1 by t minus t infinity will be equal to natural log of t minus t infinity upon t I minus t infinity. So that value equal to minus h into s upon rho v cp into the integration of del t is equal to t. So if we remove this natural log, we need to add exponential in the equation. So the equation becomes temperature at time t minus temperature at infinity equal to Ti minus T infinity is equal to e raised to power minus h as upon rho v cp into t, where this term is called as time constant. So we say that this is equal time constant is equal to HAS upon rho v cp, and the unit is 1 upon second. Now friends, we have found out the relation for the temperature distribution inside the body at different times. Now this equation we can use to find out the temperature. So this equation can serve as a two purposes. So either I can find out the value of temperature at time when when small t is given, or I can find out the time which is required to reach the temperature. Okay, now here in this relation, we are saying that we are talking about lump system analysis. So when to use this lump system analysis formula? Okay, so here comes a very important number which is called as a bio number. So bio number is a dimensionless number which can be defined as the ratio of convection convection at the surface of body to the conduction within the body. Conduction within the body. Also, I can say that this is equal to resistance, that is conduction resistance, resistance within the body divided by convection, convection resistance at the surface of the body of body. Now let us see, as per the definition, what we are seeing is the ratio of convection at the surface of the body. Now we know that the convection at the surface of the body is H into delta T, and conduction within the body can be termed as K into dt divided by the characteristic dimension of the body. So if we rewrite this equation, so we can say that this delta T will get cancelled out. So I can say that it is equal to H upon K by L. Okay. Or we are saying that it is the ratio of conduction resistance within the body to the convection resistance at the surface of the body. Now conduction resistance, this value is L by K upon 1 by H. This is the same relation that I have written on the board. Okay, so this relation can be written as 1 upon H. This H can be written as 1 upon H into this term can be written as L by K. So it becomes the conduction resistance at the body, inside the body, to the convection resistance at the surface of the body. Now, as I told you, this bio number is very important in the cases related to the lumped heat transfer. So now using this bio number, if the value of bio number is less than 0.1, we can say that the temperature within the body compared to surrounding, compared or relative to surrounding remains remains within 5% of each other. So what here we want to talk about that if the value of bio number is less than 0.1, the temperature inside the body remains within the 5% to the surrounding. So there is no change inside the body, no change in the temperature of the body. The temperature inside the body remains nearly constant if this is happening. The temperature is changing with respect to time, but temperature is nearly constant. And if so, in this case, I'll use the lump parameter analysis formula. And if the value of bio number is more than zero point 0.1, so same happens, but the temperature is more than 5%. So it means that the temperature inside the body is changing. And for the same case, I have given you an example of a very small copper ball and the chicken. So inside the copper ball, we can assume that the temperature is nearly constant. And in case of the food material, the temperature is changing with respect to time and with respect to distance. So we'll apply the lump parameter analysis to the copper ball, and for the food material of bigger sizes, we'll be using the unsteady state heat transfer and some of the charts made by Hessler and Gruber. Now, friends, there is one more important number related to lump heat transfer or unsteady state heat transfer. Now, this number is called as a Fourier number. This number tells us about the transient behavior of the system. Now, it is a ratio of heat conduction rate, heat conduction conduction rate to the thermal thermal storage. Now, heat conduction rate can be written as by the equation of Fourier we know K A delta T upon L into time. And the thermal storage can be written as MCP delta T or rho VCP delta T. So rho VCP into delta T. So what we can get, the delta T will get cancelled out, and I can write the area and volume. So this volume upon area can be term as a new term called as a characteristic dimension. So I can rewrite this equation as K A into T by rho Cp into Lc square. Or we know that K by rho Cp is alpha. So alpha into T by Lc square. Now this why this Fourier number is very important. It tells us it is the measure of heat conducted through the body relative to the heat stored. If the value of the Fourier number is more, it means that the heat is moving fastly through the body, or the propagation of heat is faster as compared to the heat which is stored. Now, our relation, that is the relation that we have derived, T, the relation was very simple. If you just look at the relation, so the relation was T of T minus T infinity upon Ti minus T infinity. So this T of T minus T infinity divided by Ti minus T infinity is termed as theta, and it is equal to e raised to the power minus Biot number into Fourier. Now, friends, this is the thing which is related to the unsteady state heat transfer. We had a discussion regarding unsteady state heat transfer, and we bifurcated into two types, that is lumped heat transfer, where the temperature in the body is termed to be constant, but it is changing with respect to time. So in case of the lump heat transfer, temperature is a function of only time. Temperature is not a function of distance. And in case of purely unsteady state heat transfer, the temperature is a function of time at the same, it is a function of a distance. So that's all for today's session. In the coming sessions, we'll talk about various aspects related to heat transfer. If you are happy with the content I am sharing on the channel, please subscribe the channel. Thank you.